If you throw them again, I will sign you up for PAC. And it's been a long time since I've signed anybody up for PAC. But I've got the spreadsheet ready to go if you make me. You throw them again, you're spending lunchtimes in PAC. Plural. Lunchtimes, plural. Okay, electrical heat and light. It's a light bulb. That's its primary job. So this, and it's a transformation from this first one into these two. Electrical is getting transformed into heat and light. Okay, cool. What's this next one?
Sound.
It's sound. And motion. So mechanical energy. You blow the air. Like, doesn't sound like a trumpet, but that's what's happening here. You go, and then the trumpet turns it into what it is. And you can change with the keys on top what turns into.
What about singing?
Singing is the same thing. Your diaphragm just pushes the air up out of your lungs, and your vocal cords change to vibrate the air differently. It's the same idea. Yeah.
So what's the difference in vocal cords between singing and
Practice would be my guess. I would say anyone could learn to sing better. Some people are just naturally better at it than others. But there are that is a thing. You can learn to sing, but some people are more naturally gifted, and otherwise it's just biology. It's if there are certain people who inherently sound better or can sing higher or can sing lower, that's their biology. They were gifted with a set of vocal cords that are more capable than other people's. Massey, do I need to be concerned? Not again. Same goes for you too, Nielsen. Have you ever been signed up for PAC? I will. Stop throwing marshmallows. Okay, even to yourself, stop throwing marshmallows. Okay, next one. Yeah. Ooh, chemical into heat and heat is so thermal is the kind of energy. Yeah, you bet. And light. So it's the chemical potential energy present in the wood that allows it to burn. It's a transformation from chemical into thermal and light. Cool. Now this one. Yeah. It turns into mechanical, and it starts as magnetic potential. And magnetic gets turned into mechanical. Because those two magnets are attracted to each other, they will slam into each other. They weren't moving before, but you bring another magnet over and they will move. Sometimes they'll just turn, but sometimes they'll actively slam into each other. Mr. Morrison has a terrifying magnet shaped like this, one of these big U magnets, where if you get your hand caught between the steel plate that it sits on and the magnet, it will shatter the bones in your hand. It is a wildly powerful. It's awesome. It's in his classroom. It's wildly powerful. It will shatter bones. Yes.
Does it matter like what order you have to step in?
No, not necessarily. As long as they're both. I'm just drawing it, and I draw the arrows from one to the other. No, the order doesn't matter as long as the arrow's in the right order. Okay, uranium-235. Who knows what uranium-235 is used for? Nuclear what? Nuclear weapons and nuclear power. So this is nuclear energy. And until we will talk about how nuclear power plants function, right now this is a potential energy because nothing's happening. It just sits there. Yeah. Why do we have it?
Yeah, if they're only used in the sun, like you said, the sun explosions.
They're not all, well, because there are certain types of nuclear reactions that you can slow down and control. That if you can slow it down and control it, you can regulate how much energy is released during this reaction, all of a sudden that becomes a harnessable energy source. The problem with, so there's two different, and we'll look at them, but there's two different kinds of nuclear reactions. One of them right now we know how to control very easily. It's called we know how to regulate it. One of the two types. It's called a fission is the kind of nuclear reaction that we know how to regulate. And if you know how to regulate it, you can slow it down to make it usable as a power source. If you choose not to slow it down, that was the first kind of nuclear bomb, was an uncontrolled fission bomb. But there's another type that they're working on right now. If you read science news, you'll see it's called fusion. Fusion right now is uncontrollable as far as a human race we know how. But fusion uncontrolled makes something called a hydrogen bomb, which is the most powerful weapon on the planet. It also is what powers stars. Stars are a fusion reaction that is, like a star, like the sun, is powered by nuclear fusion. And the only thing that contains that nuclear fusion reaction is the gravity of the sun itself. So the gravity of the sun is holding everything, pulling everything in, like the material that makes the sun, it's pulling that material in while it undergoes nuclear fusion. And so it's those two that are working kind of opposite to each other. Keeps everything contained, but the energy gets to leave to come to us as we see it as light. Yeah. Black hole is just gravity, yes. Yeah, that is the simple, about as simple as it gets, explanation of a black hole, yes. Gravity is so strong light can't escape. Yes, it is crazy. Yes. We'll get there. What's going on here? Yes. Technically, yes. Practically, no. Usually when we think of hydraulics, we think of the pressure on fluids inside. Like, your power steering is hydraulic. But yeah, but what is causing hydraulic power? Gravity. It is the gravitational potential energy. Gravitational potential that turns into mechanical. Because it's moving. The water at the top there only falls because gravity, because it's at a place where there's nothing supporting it, and then it starts to move down. You could then allow something, you could put something in its way, that something would spin. That's the whole premise behind a water wheel. Or a hydroelectric dam, is just falling water spins something. And the something that it spins is a little bit complicated. Okay, what's going on the left there? It's not mechanical because it's not moving. Kaylee, what is it? It is elastic. That is a bundle of letters held together by what's supposed to be a rubber band.
That's a rubber band?
Well, look how it crunches it in there.
Well, I thought it was a spiral or something like that.
It's supposed to be. That is some of you guys maybe have never seen a bundle of letters in your life because, that doesn't happen very often anymore. That's supposed to be a rubber band. Jedediah, what's H?
Oh, chemical.
Burger and fries. This is chemical potential energy. The burger and fries does nothing until you eat and digest it. Cool. What's the next one? Ooh, that's a hard one. It is mechanical.
Is it a bullet?
You tell me. Look at it. It is a bullet train. What powers a bullet train? What kind of types of energy? It is not potential. It is not electric potential. Someone else said it already. You're right, it's magnetic. Whoever said magnetic, I heard it twice. It's magnetic that gets turned into mechanical. Basically what happens on a bullet trains are really cool. Basically what happens on a bullet train, for those of you who want to know, there are magnets, electromagnets, and north, south, and on the train, there are magnets, and if you're aware of magnets, a north pole is attracted to a south pole. So this one will be a south, that one will be a north, that one's going to be a south, and that one's going to be a north. The beauty with an electromagnet is that depending on which way you flow the electricity, you can change the polarity of a magnet. And that's how a magnetic bullet train works. These will swap. If you make this one a south pole and this one a north pole, this one gets dragged forward by this one. But then if you flip it and make this, so if this one over here is a north pole, this magnet is attracting this magnet forward and it's pushing this magnet away. And if you change the electric current that's running through these electromagnets, you can cause them to flip back and forth so quickly that they just drag the train forward. So it's not actually on wheels, it's just hovering there. Kaylee. Yeah, these are the tracks, this is the train. Yes. Yes. The opposite. If you make this one a south pole, then this one is going to be attracted backwards, and this one's going to be repelled backwards. So just like you can flip them so that it drags the train forward, or you can flip them the other way so that it slows the train backwards. It's a really cool system. It's wildly high tech, but it's very, very efficient. There's no friction, none. But if you lose power, you're screwed. But are you? Because if you lose power on a magnetic train, the train's just going to slam down onto the tracks and skid to a stop. So it's actually wildly safe. Like, you're not worried about derailing. You don't have to deal with the friction. It's very cool. And if you can make it worth your time to invest, it's expensive. But if you have a reliable source of power, like Japan and China pioneered these things. Japan is largely nuclear powered. If you have a large source of available power and the technology to make it happen, it's sweet. Okay, so we had this page as well. The picture's not as necessary because the descriptions are here. You've got an MP3 player playing sound. It's electrical to mechanical to sound. Mechanical because it's vibrating a speaker. Sound because you hear those vibrations. That's how headphones work. The throwing of the ball. What's going on there? Kinetic is the result. How do you throw a ball? Sorry, Kaylee? That's the result, but how do you get to that point? Brooklyn. You throw what kind of potential energy? It's not gravity. There's no such thing as physical potential. Sorry, Amatosh? Elastic where? In the muscles of your arm. And where does the elastic come from? What allows you to move your arm? No, well, yes, but no. Nope. What allows you to move your arm? The food you consume gives you the energy to do what you need to do. So stupid. It's not stupid because we're learning together. It's the same as a ball being thrown. Your muscles are not rigid. Your muscles are elastic. I mean, that's why you want to warm up. You want to warm up your muscles, whether it's cold or not. Like, it could be a hot day outside, but if you're not prepared for physical activity, that's why we stretch. That's why we do some warm-up laps. That's why you get yourself ready so you don't hurt yourself, to increase the elasticity of your muscles, because if they're rigid, then they tear. And if muscles tear, I mean, that's the premise of working out, is by tearing micro tears. But if you have massive tears, then you have a McWhinnie. Was anyone here when McWhinnie did his McWhinnie? Mr. McWhinnie tore the biceps off his bones. I don't know which bicep, but he tore the bicep off his arm. I can't remember if it was last year or the year before. That's why I asked if you guys were here. He went to do a chin-up or a pull-up, and it happened here at school. His bicep detached, and the whole thing rolled up inside his arm. Yeah. He's still recovering from that injury. But your muscles are elastic. If they snap off where they're attached, they will roll up. It's gross. Very, very gross. Yeah. Yeah. And wildly painful. The muscles in his arm went snap.
Did he warm up though?
I wasn't there when it happened. I just know the results. Wildly painful. Okay. Hot food sitting on the table. The hot food is just sitting there. It has chemical potential. It actually ends with chemical potential. See, and this is the problem with physics. No, gravity has nothing to do with the hot food sitting on the table. It's thermal, because it's hot. Thermal to chemical potential. The food has been cooked, now you can eat it. This is the problem with physics, and I tell this to my physics students all the time. Physics 11, Physics 12, those courses, their sole purpose is to break down what you think you understand about the universe and build it up the way it actually is. And the more resistant you are to that procedure, and it's worse with physics than any other science. There's so many other sciences, you walk in there assuming you don't know how things work, and you're like, teach me chemistry. Teach me biology, because I don't know how things work. People walk into physics and we start really, really simple. And they're like, I know how this works. And I sit here as the teacher and I say, do you really? Because I've spent 15 years unlearning everything I thought, longer than that. I got into university in 2006. 19 years unlearning how I thought the world worked and rebuilding from the foundation of the lens of a physicist. And you learned from your parents, and your parents, unless you do have parents that are engineers, are probably just going from their best understanding of the world. But how many of you, when you asked your parents why the sky was blue, talked about something called Rayleigh light scattering? Have any of you ever heard of Rayleigh light scattering? I saw one person nod. My 4-year-old has heard about Rayleigh light scattering because she has a father who studied it. And so my daughter, my 4-year-old, at least she does not understand it, because there's so many parts along the way that you don't understand, but has been told properly why the sky is blue. And that's because wavelengths of light bend at different angles. Red light bends up and out. When the sun is high, it's the blue light is the only light that makes it through. When the sun is low in the sky, all of a sudden, the yellows, the oranges, the reds, because of the angle the sun is at, are allowed to bend through, and the blue reflects light. This is exactly my point. You're proving my point perfectly here, Evelyn. The ocean has nothing to do with it. And so you spend your entire life being taught very simple truths incorrectly. And so physics requires you to disassemble and rebuild everything from first principles. And physics might be the only class where everyone walks in with the arrogance to say, I know everything, regardless of whether or not you actually walk in and say you know everything. People don't say that about math. People don't say that about English. People don't say that about biology or chemistry, but physics they do. And it's being willing to tear everything down and start over that is why you sit there and say, this is stupid. Because, and I've been there, I totally empathize with that frustration. But that's what physics is. It's being willing to be like, everything I know is wrong, here we go. I have to be willing to start from nothing. Okay, I'm not going to go through the rest of these because so much, you're getting the understanding that so much of this is the same. So let's flip ahead. And we're going to use the 25 minutes we have left. We'll do a couple examples and I've got some practice for you to play with. Okay, so you stay on this page. I'm going to flip back a couple pages. When we discussed mechanical kinetic energy, so the energy of a moving object, we said, we agreed. I held things above heads and I talked about moving around. We agreed that as a class, the thing that sucks about a moving object and the thing that's going to hurt you when the moving object makes contact with you are these two things. If you have a low mass object and a low speed object, it's probably going to be fine. But you take a low mass object and you speed it up, it's going to have more energy, it's going to hurt you. If you have a high mass object moving at low speeds, it still could mess you up because a high mass could still trample you. But if you have a high mass object moving at a high speed, that's definitely scary. And we intuitively understand that speed is the bigger issue here. Because you can take a low mass object, speed it up, it'll suck. You can take a high mass object, it'll already suck, but speed it up, it'll suck even more. So the equation, and I'm not going to explain where it comes from because it's complicated. At this stage, you need to take my word for it. The equation that governs mechanical kinetic energy is this equation right here. EK, sometimes it's given as KE, stands for energy kinetic or kinetic energy. Kinetic energy is given by this equation. 1/2 times the mass of the object times the velocity of the object squared. And so you can see here by the math, the thing that makes this thing terrible is that squared number right there. If you recall, squaring something means multiplying it by itself. So if you have a large velocity and then you multiply that velocity by itself and then multiply by the mass of the object and then have it, you're going to see that things get really bad for you very quickly. So this is the equation that we're going to get comfortable using. Where it comes from will be explained to you at some point in the future when you take physics. It actually requires you have a working understanding of calculus. So where it comes from probably won't be explained until your first year of university, should you choose to study physics. So at this stage, you have to take my word for it. It's actually, and to prove to you that I know where it comes from, it's the integral of momentum. What's momentum? Mass times velocity. You take your momentum, you integrate it over a period of time, and now you have mechanical kinetic energy. What does it mean to integrate? That is for a later math class. So let's use the equation. How much energy does a 20 kilogram koala have crawling at 5 meters per second? Now, this word crawling is terrible. The other thing that sucks about this is this idea of meters per second. If you look at the equation here, when we use mass in physics, we have to be in kilograms. You have to be. It's just a rule. When you're dealing with velocity, you have to be in a unit called meters per second. Now, you guys probably don't have an active understanding of meters per second because you guys are used to kilometers per hour. So just so we're clear, a kilometer per hour, if you want to go from kilometers per hour into meters per second, what you're going to do is you're going to divide by 3.6. Again, where this comes from doesn't matter at this stage. This you'll learn next year. Take my physics class, grade 11. I will teach you how to do this conversion. But what this means is, just to give you some perspective, if you're traveling at 100 kilometers per hour, so highway speed limit, that is equivalent to 27-ish meters per second. So if a koala is crawling at 5 meters per second, just so we're clear, here's 5 meters. I will demonstrate 5 meters. show you how ridiculous that is. If you've never seen a koala, they're slow and fat and stupid. I know this because I've held them. I have close personal knowledge of koalas. They're so stupid. And all of them, fun fact, all of them have chlamydia. Yep. The STD chlamydia, all koalas have. Okay, so koalas, small, fat, little gray, stupid bear. They don't move very quickly. This question is suggesting that the koala started here and ended here in that much time. 1, 1, 1, 1, 1, 1, and the koala is moving this distance on that beat. Not possible. Koalas cannot do this. To put this into perspective, in your car, this is like going 18 kilometers per hour. 2/3 of school zone speeds. Koalas can't move that way. If it could, how much kinetic energy would it have? So, EK is equal to 1/2 mv squared. I am going to model how you do physics calculations. The first thing you do is you write out the formula. You don't plug anything in. Write out the formula you're going to use, because I'm going to give you 3 different formulas over the course of this unit. You'll have one for kinetic energy, you'll have one for spring potential, and you'll have one for gravitational potential. Write down the equation that you need to use, and write down what you know. We know that the mass of the koala is what? 20 kgs. We know the speed or the velocity at which the koala is moving. How fast is the koala going? 5 meters per second. And now we can take those and we plug them into the proper spots in our formula. When you plug them in, you replace the letters with brackets so that everything gets handled properly. So this, and you put it right below where you wrote the equation to organize your work. 1/2, the mass is 20, in brackets, the velocity is 5, close the brackets, squared. By organizing your work, you make sure you don't lose anything, you're not missing any pieces. Don't rush the process. If your math teacher has never been this intense about things, they should have been. And now we can go ahead and we can do the math. The answer here, of course, is what? Well, I mean, you don't need a calculator for this. You shouldn't need a calculator for this. What's 5 squared? So this is 25. What's half of 20? What's 25 times 10? 250 joules. You are welcome to use a calculator, but often the numbers will be nice such that you do not need them. Okay, do we have any rugby players in the house? Okay. Would you two be so kind? Oh, Brooklyn, you're not a rugby player? Oh, you were just saying that there was a rugby player, and it's Sarah. Okay, Sarah, can you come over here for a second?
Don't label me next class. He's not running clearly.
Okay, no one's gonna look. Just stand on the thing. Yeah. Tell me if it's higher or lower than 75. Interesting. Not. Yeah, lower. Much lower. Okay, so hold on. Get back over here. I want you to hop back on there. Holding this box of heavy things. Okay, hop on there. Oh, okay, hop off. Keep holding that thing. Ooh, no, don't. Oh, bring that thing back over here. Okay. Actually, you know what? Okay. Put that on the desk right here. This is not light. Try it. If you have struggle with it, are you good? Okay, get on the scale. Okay, just so we're clear on what's going on here. Oh, now that's 8. Cool. So Sarah plus all of these masses is basically what we're talking about here in the because you guys are often not comfortable with kilograms. So just to give you perspective, that's what we're talking about. Sarah plus that box of masses. How much kinetic energy does that person have running at 10 meters per second? So the ground here, that was 5 meters. 10 meters per second is twice as fast. 10 meters per second is, just so we're clear, not humanly possible, because 10 meters per second is 36 kilometers per hour. Usain Bolt doesn't run at 36 kilometers per hour. Like, this is beyond possible human speeds. So Sarah, if you can imagine running faster than the school zone, carrying that box, that's what we're talking about here. The numbers are ridiculous. How much kinetic energy would that person have? Well, EK, model it again, 1/2 mv squared. We know the mass is 75 kilos. The velocity is 10 meters per second. The numbers are ridiculous. Plug them in and solve. It's just substitution. There's no algebra yet. The algebra's coming later. Times 10 squared. Again, I mean, this one, the 75 here messes with things. So let's make this easier. Instead of 75 kilograms, let's make it 80. Because that makes these numbers a little bit nicer. Yeah, man? Yeah. You bet. 80. Because actually, with Sarah and the box, it was 80. So we're making it a little bit more. The numbers here are going to be nicer. You too, man. Half of 80 is 40. And 10 squared is 100. So how much energy does that rugby player have? 4,000 joules of energy. Which one of those should you be more afraid of? The rugby player coming to get you, or that koala coming to get you? No, I assure you they're stupid. Yes, Brooke. Joules. That is, whoops, my bad. So energy, when you quote energy, energy is measured in joules. Yeah. Because it is. Thus saith physics. So we use a bunch of different names. So Joule is a physicist, was a British physicist, and he gets the honor of being named for these units. Force is another thing that we talk about in physics. Force is measured in newtons because of Isaac Newton. Power is measured in watts because of James Watt, British physicist. Like, we take names of people who had significant contributions to the field, and we attribute their name to the unit. Meter is a French word, don't know what it means. Gram is an English word, I believe. Might actually be French, though. Ooh, I shouldn't say that. Anyway, it's the joule. The J stands for joules. It's the unit with which we measure energy. Distance is meter, time is seconds, energy is joules. Okay, last one, and then you're going to play. Which of the following has, I think you're going to play. Yes. Which of the following has more kinetic energy? A golf ball moving at 900 meters per second. Just so we're clear. Yeah, it's beyond possible. 900 balls. That is, just so we're clear, 3,240 kilometers per hour. That is, just so we're clear, speed of sound in kilometers per hour. No, in, yes. Okay, and just so we're clear, this is actually really interesting. For anyone who's into aviation, this is, if I've done my math correctly, and I think I have, Mach 2.6. So 2.5 times the speed of sound. Just over 2.5 times the speed of sound. So again, beyond what a golf ball is capable of flying, But let's say you got a golf ball going 2.5 times the speed of sound, or you've got a 1 kilogram ball moving at 10 meters per second. 10 meters per second is 36 kilometers per hour. So we're clear. Obviously, which one of these is going to have the higher kinetic energy? You don't even need to do the math. Think about what's happening. I'm going to square 10 and multiply it by 1, or I'm going to square 900. 900 squared is 81,000. It's not even close. So let's make this more realistic and make this 90 meters. You know what? Forget that. Let's make it, 90 meters per second. Still really fast. Yeah, but see, that's why you shouldn't work ahead. 90 meters per second is 320 kilometers per hour. This is a lot more realistic. Still beyond what a golf ball is going to do. But basically, this is like muzzle velocity for most firearms. If I'm not, no, actually, it's well below that. Hold on. Speed of golf ball in. Oh. Seriously? Nice. This is basically an accurate speed for the golf ball being driven down a golf course. So let's just play this up. Which one's gonna? Now the numbers are a lot harder to judge. Let's look at the kinetic energy. EK equals 1/2 mv squared, and I know the mass here is 0.01 and the velocity is 90. So we're going to get 1/2 times 0.01 times 90 squared. What is that value? What's the final answer? I want you to give me the final number. What is 1/2 times 0.01 times 90 squared? Messiah, or wrong class. Jedediah, do you have an answer?
I don't know, but my math is like 40.5.
That is correct. 40.5 joules. That is the kinetic energy of the golf ball. Let's take a look at the 1 kilogram golf ball moving at 10 meters per second. Okay, so EK equals 1/2 mv squared. 1/2 times 1 times 10 squared. That should be easy to do. What is 1/2 times 1 times 10 squared? That is 50. So that 1 kilogram ball moving at 10 meters per second has just a little bit more kinetic energy than the golf ball moving at 90 meters per second. But it's close. A 1 kilogram ball would be, well, 1 kilogram is 2.2 pounds. It's a small, like a really small bowling ball, like a 5-pound ball, or a 5-pin bowling ball. 1 kilogram is roughly 2.5 pounds. A 5-pin bowling ball, moving at 36 kilometers per hour, would do more damage to you than the golf ball moving at 90. Golf ball's still going to hurt. Bowling ball's going to hurt more. Okay, flip the page. You have 6. There is less than 10 minutes left, so I can't let you go. I'm really sorry. Flip the page. There's 6 questions I want you to take a look at. Let me know if I can assist you. On your mark, get set, go. Yes, sir. I cannot let anybody go unless it's an emergency. There's less than 10 minutes left. I can't let you go.
It is an emergency.
Massey, is yours an emergency too, or do you just would be nice? Not an emergency. Okay. If it's an emergency, you can go. Okay. There you go. Play with those. Yeah, go pick it up. Okay. Okay. Set your work up the way I demonstrated. Don't get sloppy. Okay.